Hello guys online. I'm very sorry for not unmuting myself. Um, so yeah, it's okay. Just a bit. We have just used 20 minutes. You can still learn a lot in the rest of the tutorial. So yeah, so we have just talked about the visualization of prompt learning. It's very difficult, and next we would like to know whether prompt learning can generalize to broader concepts, right, within the same data sets, of course. So what we do is that we learn some prompts on the base data sets, such as these scene classification data sets, where we have these arrival gates, procedural list classes, right? And then what we do is that we actually apply the prompt to different classes within the same data set, right? So in this case, we want the prompt to actually capture some attributes or properties about scene classes for scene recognition. So ideally, we want the accuracy to be maintained. But actually, in doing so, what we found is that prompt learning can completely fail in the classes that have never been observed during training, although those classes are within the same data sets. So the problem is the prompt only works for a set of classes, right? It means overfitting. So this not only happens in one data set, but also in other data sets with different classification natures, such as ImageNet, Caltech for object recognition, right? And also the some specialized data sets, such as DTD for textual recognition, and also action recognition on UCF 101. So what is a good prompt? So we argue that a good prompt should categorize each instance specifically using some context words. So what does this mean? So what we want, so the images are the same, right? So what we want to tune the prompts by actually pushing the text features towards the image features. In this case, the text features and the image features, they are well aligned in the embedding space, right? So in this case, if we have this image, we want to classify it. We want the prompt to contain some context words that are relevant to this image, like a person riding a motorcycle on a dirt road. And the same happens to these images, where we want this prompt to contain some keywords such as in the grass, if we want to classify this image as dog. So technically, in order to realize this idea, what we did is we designed this conditional architecture where the prompt tokens are actually conditioned on the image features, right? So here you can see we have this meta net that takes as input the image features and then generates some so-called meta token that is replicated to the number of context tokens you have in the prompt. Then they are combined with the prompt to be given to the text encoder. So here the main idea, here the simplicity is that because each token is a vector. So normally we need to have like the multiple neural networks to generate different tokens in order to combine with the prompt tokens. But here we only have one meta net that takes as input the image features and generates these tokens that are shared by different prompt tokens. Right, so we found conditional prompt learning is very generalizable. The results are much better than the COOP in unseen classes, right? But it's very slow to train because the conditional design and sorry for the delay. So yeah, we have a result showing that conditional prompt learning is more generalizable, right? And yeah, but it's very slow to train because of the conditional design. So in order to solve this problem, actually, we can do is that we can do multimodal prompt learning, where we have where we can learn some parameters in both of the input spaces, both the text and image feature space, right? So we have this multimodal prompt learning architecture that is essentially a transformer neural networks. So it's a multimodal learning approach that is more efficient because it doesn't have the conditional design. Right. So in a case where you have more compute resources, right, you want to not just tune the prompt tokens in the input space, you want to tune the entire vision transformer. So what you can do is that you can actually use neural architecture search. So what you do is that you design a search space by embedding this prompt token, different prompt modules like adapter, LoRa, and VPT, visual prompt tokens, into different places, and use your favorite neural network architecture search algorithm to solve this problem. So on the right-hand side, what we see is that our approach NORA actually performs better than the other individual prompt models on most of the data sets. And we have just talked about white box prompt learning, right? It means that you can have access to the large-scale vision language model. But in the case where the model is given as an API, how do you solve this problem? How do you train your prompt, right? So we call this black box prompt learning. So in this example, we have the API, we have a large-scale vision model that can actually do image segmentation by if you give a prompt, right? You give an image and you give an example, and you also have this test image. The model can automatically fill the missing patches by giving you the desired segmentation image, right? So in this case, you only have the API. So the problem is, how can you learn this function that can actually select the optimal prompt from your data sets? So here the main idea. So here the main idea is that you can design this function by using API as the supervision signal, right? So you give some test images. You have some test images from your source data sets. Then you basically use the API to score each of the source images by basically produce some segmentation images for different source images. Then what you can do is that you use this as a supervision signal to optimize your score function, right? So here we don't get into too much details about this work. So that is the end of this session. The take-home messages are here. So here I will not repeat those sentences. You can take a look. So we almost run out of time. So here are the references for the papers that are mentioned in this the first part of this session. And here we have a code available on this link. You can just go to the link and find the code and play with the code. So yeah, that's the first part of this first tutorial, and we may have some time for a couple of questions if you have about this prompt learning for visual language models. Right, so it's okay if there's no, yeah, so if you, I think some of you might have played with the code before, the prompt learning code. So if you have any question, you can find me offline. I can help you debug, right? If you need some help. Okay, so it's 9:30. I will hand over to Ziwei, who will talk about prompting in visual generation.
Okay, so thank you everyone for coming. I think Kayan has covered much of the different works in this visual intelligence, that is in recognition, detection, segmentation. And another very important aspect for this prompting to work in computer vision actually lies in this visual generation, right? So everyone works in this generative AI now. So how can we use the prompting also in generation? So I will use just about like 15 or 20 minutes to quickly go through this field. So actually prompting is have done a lot of different jobs in this generation. So you can see generative models can work for images, videos, 3D, and even 4D recently, right? So and prompts can take different forms. So the most like the popular form is like the text prompts, like this cocky here, right? A different kind of a fancy dog. And also prompt can take different forms like images or even mask or even sketch, right? In the context of generative models. So here we are also covering how we can convert different forms of like images, sketches, masks into these continuous prompts. So this is kind of an overview of this prompting in generation. So I will just give an like a tutorial on this representative works in each of the field. So the first part is this text to image generation. So I think you should be very familiar with this part, right? So like give a prompt, an astronaut riding a horse in photorealistic style. So you can like instantly get all these images. So it's from the DALL-E 2, this kind of the paper. So how can we just get to the point where we can create so photorealistic images? So there are several works. So I will just go through them. So it's actually, there are some Wikigam-based method. So that kind of try to build in the link from a text, the prompts, to this discretized, this placed in this vector quantized latent space. And then we have this very popular diffusion-based method. And we also have this, the GAN comes back, right? This GAN-based method. And I also talked about how we can use the ideas on very specific kind of data, like how can we train some prompt-based generation on like human-centric data. So the first is the very like the DALL-E work, right? This kind of a very pioneer work in this visual generation using prompt. This paper, this zero-shot text to image generation. So the main idea is pretty straightforward. So you have some image, you use this kind of a VQVAE, this variational autoencoder, to code all the image information into this codebook. So we have some vocabulary size. And then how to do the generation is kind of like retrieve the indices from the codebook and try to use the decoder to synthesize image. So how do we like make the synergy between text and this synthesize is there are some clip inside that tries to bridge the text with the codebook. So that's the main idea, right? So after DALL-E work, then people tries to like doing more advanced different diffusion things. And here is more like the second stage, that is how to learn the prior. So the prior, you can see here, we have some sentence like the well-known surrealistic piece introduced the image of the soft melting pocket watch. So it's the text, and you have some encoder to the tokens, right? Then the token, the text token plus your visual tokens, that is a prior learned in your autoencoders together, then you fed into some transformer, you get your final representation, right? So you can see it's pretty straightforward. So how to do the prompting in generation. So people first doing is first transform the text to some tokens, then learn some image priors. So the prior here is encoded by this VQVAE. Of course, you can use diffusion as a prior, GAN as a prior, so both are fine. So the first work is using this kind of a VAE, then you try to fuse them, you use some transformer, you get the final results, right? So that's the general idea of how to do the prompting in generation. And there's some work improved, it's called the glide. So I may skip all these formulations. So it tries to introduce this diffusion as a prior. But the main take-home message is the use of this classifier-free guidance, right? So there's a lot of different guidance in like diffusion models. You can use clip guidance, classifier-free guidance, and the one conclusion in this work is that this classifier-free guidance is more preferred by human evaluators for both this photorealism and also the caption similarities, right? So here's the main takeaway message. So after these two works, then DALL-E 2 comes, right? So DALL-E 2 actually have also the same like framework as the DALL-E 1, that is the prior network as well as the decoder network, right? Of course, let's introduce some clip things, right? Clip tries to build the connection between the text and the image. I think Kaiyang has already covered this part. So after this part, it has another prior network and decoder network. So it's essentially similar to DALL-E 1. Expect that the prior is captured by different things. So the decoder here is also a diffusion model that is directly operated on the pixel space, right? Of course, you can use like latent diffusions. And you can also have this autoregressive prior. So I think a lot of the works, they like rely on this autoregressive things. So for this work, it's the prior comes from the diffusion model, the decoder is from diffusion model, and all the things are autoregressive, right? So it's much more like this large language model nowadays. So then comes this stable diffusion, right? So instead of we capture the prior in the pixel space, so how about we just capture prior in the latent space? So the idea of this kind of latent diffusion model, this paper, is actually tries to first learn the latent space, to encode image into the latent space. Then we just do all the diffusion, the edit noise, the denoising process in this latent space. So it has two advantages. The first is the image has been encoded into some like decoupled representations. The second is that it's much more efficient. If you want to do the diffusion on the pixel space, it's you need a lot of GPUs and it's pretty slow. And if you want to do this diffusion on the latent space, so sometimes you get faster convergence, and also you don't need that much computational resources. Of course, in the era of like the diffusion model, the GAN can also comes back. So here's work from like the scaling up GANs for text to image synthesis. So it's kind of convey the message that's like the diffusion model, like all we need, right? So it said that GAN can also do the things. You can see it replaces the prior part with the GAN model, and also using some text encoders, right? You can see the local and the global text encoders also tries to fuse the information into each like layer, each different levels of space in the GAN models. And when you're doing this like multi-level things, you can do a quite good job also synthesize images. So the message here is that maybe diffusion model is not like that kind of advantages over other alternatives. So GAN can also do a good job with like tuned correctly. So finally is that how can we like build in this text to like the image into a specific field, like text to human. So here you may want to use the prior inside that field. So for humans, it's a natural idea is to separate the humans into shapes and textures, right? So maybe you can learn two separate networks. One like autoencoder for the shape, another autoencoder for the texture. So get different code books. You also try to link the text with different code books. So in that way, you can do a much better job than just using a general diffusion model or general like the text to image models in a very specific field. Okay, so that's our first part. It's more on this text to humans. So the second part is on this image prompt. That is, besides we use the text to generate image, we can also using image to generate image. So like one image is worth 1,000 words, right? So we can transform the image into some prompt. So there's like two different kind of track. So the first is prompting for appearance generation. So you give it some images and it tries to generate new images that is similar to the appearance given by the exemplar images. So they have two different kind of methods. The first is optimization based. So it's slow, but the quality is better. Another is encoder based. So this is very recent works, just appeared in last 2 or 3 months. So they're fast, but the quality is still not close to the optimization based yet. So it still has room for improvement. So the second track is on this prompting for relation generation. So sometimes we not just want to mimic the appearance in these example images. We also want to mimic the relations and some high-level visual concepts in the images. So it's like the prompting for relation generation. So we will first talk about the optimization based for appearance generation. So the kind of the first pioneer work is the textual inversion. So you can see we are given some of the samples, right? We're given 4 sample images, and we want to invert these sample images to some prompt. So here is using S* to represent this prompt. Then we can using this prompt for generating new things, like an oil painting of S*, F icon of S*, or this like the Elmo sitting in the same pose as star, right? So you can generate new things using a concept that is not conveyed using text, but conveyed using these images. So the idea is pretty simple, just like what Kaiyang has like introduced in the visual intelligence, visual recognition. It also tries to optimize continuous text tokens, right? So the key idea is just this formulation. You try to optimize the text tokens so that these tokens are very close. So in a latent space, very close to your exemplar images, right? So however, it's kind of an optimization based method. So it's pretty slow to find such a prompt. Then there's another work, it's the Dream Boost. I think also will be appearing in this CVPR, this fine-tuning text-to-image diffusion models for subject-driven generation. So it's still an optimization-based method, but it does one very important improvement. It is that in the textual inversion, you only find the text tokens. So the model is frozen. The model is frozen. So just like the COOP work in, I think Kaiyang has just introduced, you just froze the model, you find the prompt, find the tokens. So for the Dream Boost, it tries to also fine-tuning the model. So that's one important trick to improve the quality. However, to fine-tune this model on just a few images, so it's like a few shot generation settings, you only have like 4 to 10 images. So to a little overfitting, right? So it has another loss that is called the prior preservation loss. So that's your network not overfitting, like while fine-tuning to your personalized data. So that's the one very important trick here, that is fine-tuning to obtain a personalized text-to-image models here. So given some image, you can make the quality in different like places. And there's another part of work that's called encoder-based method for this image prompt. So it's more very recent work, just appears like 2 or 3 months like within like this year. So encoder-based method is generally faster because it tries to find prompt using a feed-forward parse. It's not tries to find prompt using optimization. So the recent work such as tuning encoders like the Elite or taming encoder. So they are all like the archive papers now, they have just like appeared in archive like very recently. So they are quite fast. There are a few optimization steps and they are memory efficient. You don't have to maintain like a large like gallery sets there. And sometimes also enables one-shot generation. You only need one image to find the prompt, right? One image to find the prompt. So for this like tuning encoders, instead of you trying to optimizing some tokens, some prompts to represent your exemplars, you actually learn some encoders. So here, this work, it tries to propose some domain-specific encoders. So it has some assumption. You like have like certain categories, then you learn some domain-specific encoders. Then you use the encoders to find the final prompt you want. And also it learns the weight offsets. So it's another way to prevent overfitting. Instead of tuning the whole weights, you just find the weight offsets. So that's also a clever way to do it. So another work is called the Elite. So I think Elite is more improved upon the first work, right? So instead of just using one single encoder, it's using like 2 networks. The first is called a global mapping network. It tries to find the coarse semantic meanings. Another is local mapping network. It tries to find the details. So it's using two networks, two encoders to capture the meanings of images, to convert images to prompt. And the timing encoder, I think, is adding more tricks. The first trick is using some off-the-shelf segmentation models, right? So now you have segment anything. Maybe you can just segment your foreground. So you get some background removal and adding the encoder, of course, adding some triplets loss, right? Some triplets preparation schemes inside. So the three works are very recent works, like represents the advances in this field that people trying to find very fast this adaptation method. So you have a handful of images, sometimes a one-shot scenarios. Maybe we can just learn one encoders to encode all these images to some tokens or prompts. And the second track is like the prompting for relation generations, right? So the first track is appearance generation. You had a handful of images like the dogs, like the cat. You want to synthesize the same dog with the same cat. So how about we have a handful of images, like example images contains these relations instead of appearance, like the cat is contained inside the box, and the rice is also inside the bowl, and the dog is inside the basket, and finally the vegetable is inside this paper bag, right? So maybe you have just these 4 example images. Can we also learn some prompt, some continuous prompt that can represent these relations and synthesize new images that mimic this relation? So the answer is we can do it. So the work is this reversion, diffusion-based relation inversion for images. You can actually also using optimization-based method or encoder-based method to learn these coexisting relations in example images here. So once you have learned this relation prompt, this R here, you can reuse this R to generate relation-specific images. So like the Spider-Man using the R in between the basket. So it's Spider-Man is inside the basket. So I think this work also showed that the original stable diffusion is very hard to capture the relations between different subjects. So by using this learned relation prompt, you can synthesize new things here. Like the hamster is inside the paper bag, rabbit inside the cup, so you can do a lot of the different things. So of course, beyond this, the text prompts and also the image prompts, we can have more prompts, like the mask, like the sketch, right? So we can have the difference for different modalities. So each modality can serve as a new prompt. So if we have so many prompts, so can we unify them using the same framework that take different prompts inside and tries to generate the final results? So the answer is also yes. That's another work in CVPR this year. So it's called the collaborative diffusion. So try to use in this multi-modality prompts, sometimes using math, sometimes using sketch, sometimes using text. So you try to unify them together. So I think the general idea is that inside the denoising process of the diffusion model, you can actually try to fuse some of the intermediate information inside, right? So that's a cool idea. So I think due to the time, I will just stop here. So so in my sessions, I've talked about how the prompting can act in this image generations. So the prompts can take different forms, can take the text, take images, can take different forms. Okay, right. So thank you guys. That's my part.
Okay, so the next session will be given by Danny Zhou. So Danny is not here. You give the talk online. Let's see whether. Okay, Danny is here. Hello, Danny. Can you hear? You're on mute.
Okay, can you hear me now?
Yes.
Awesome.
You can try sharing your screen to see whether it works.
Can you see my screen?
Yes.
Awesome. All right. Hello, everyone. I'm Danny, Principal Scientist and Research Director in Google DeepMind. And I founded a reasoning team and currently lead it. So today I'm going to talk about teaching language models to reason. So unlike Kayang and Ziwei's talk, so my talk is text only. So let's first spend a few seconds to think about what would you expect from AI in the future? The possible options could be like self-driving cars, digital assistant, and so on. To me, actually, I have little expectation from AI. AI should be able to learn a new task from few examples, like what usually humans do. So does machine learning meet this expectation? During the past decades, the community have developed many techniques like semi-supervised learning, transfer learning, meta-learning, and so on to improve data efficiency, of course. Despite those fancy names, unfortunately, none of them really works in practice. The failure actually made me frustrated, but also motivated me to think another question. What's missed in machine learning? After years, I figured out the answer: reasoning. Humans can learn from few examples because humans can reason, not because data structure, manifold learning, or low rank, or those stuff. Now look back, the answer seems so obvious. And we also found a simple way to solve reasoning, teach language models to reason, like teaching our kids. Let's start from toy problem. This problem is called last letter concatenation. Given people's name as input, the output is the concatenation of last letters of the first name and the last name. For example, given name Elon Musk, the output is NK. Since the last letter of Elon is N and the last letter of Musk is K. If we want to solve this by machine learning methods, we need tons of labels to train a specialized model. How to solve this problem with large language models, or LLMs? So first, let's talk about what large language models are. LLM is a transformer model trained to predict next word. For example, give a sentence, AI is the future, and the user AI is there as the input. Then the LLM is asked to predict the next word, which is future here. If the model made a mistake, then we adjust the weights. That's it. We can train the model with many sentences. For example, using all text from the internet. That's all we need to train a large language model. You can think of training an LLM as training parrot to mimic human languages. Once we have a trained large language model, then we can use whatever as the input. For example, to solve our problem, we can concatenate all the examples and the test question together as the input. And then we'll see what will be the output from the large language model. Here's the result from GPT-3 model. Actually, it's GPT 3.5. This is a playground by OpenAI. So we see Elon Musk, NK, and Bill Gates, LAs. So what will be the output of Barack Obama? The output shows to be MA. Failed, right? The correct answer should be KA. Okay, then one wonder, okay, why not just add more examples and see how it works? Here's a show, okay. Again, there's also still wrong here. So more results are not, more examples are not helpful. When I founded the vision team in Google, and I created this task as a goal to solve. So you may see my motivation here. Why I created this task? To make machine learning fail and to make few-shot prompting fail, while this problem is trivial for humans. We propose channels for the prompting. Let me show you how to use channels for prompting to solve this task. COT actually is very simple, adding thought before answer. For example, in the first exemplar, Elon Musk, instead of showing the answer NK, we also add our thought before the answer. The text in the red box, the last letter of Elon is N, the last letter of Musk is K, blah, blah. And also similarly, we can do the same thing for Bill Gates. And then concatenate all that together as an input to large language model and see we got correct answer now. That's exactly what we want. The output now is Ka, and also the thought process is correct. As one may expect it, one example is enough, just like humans. Actually, this one example can get accuracy 100% for this task. Here's a side-by-side comparison between future prompting proposed by OpenAI in 2020 and channel for prompting by us in 2022. In standard future prompting, it's just input-output pairs, but for channel for prompting, we add rationale between input and output. That's the only difference. In Google I/O last year, our CEO Sundar announced channel for prompting together with our new language model, PaLM. We first witnessed the power of channel for prompting from PaLM. And then we verified channel for prompting on GPT-3.5. So we observed dramatic performance improvement. And actually we achieved sold-out results on almost any task we tried. So now let's see how to use large language model to solve math word problems. Again, if we just show the problem to the large language model, it will fail. Right? You see 5 apples. That's not the correct answer. So now we see what's the magic of chain of thought. We add example with thought. And then the model can generate correct answer. The highlighted text here generated by Tag DaVinci Z3. So from the demonstration example, you will see, okay, we just need one step to solve that problem. But for the test problem, it needs 2 steps to solve. That's an amazing generalization. Interestingly, the similar idea appeared before. So actually solving math word problems is a long-standing problem in NLP. So even in the 2017, DeepMind has published a paper, and they use question, rationale, and answer to construct the data set. And no one did similar work before, and even no one did that after. Until 2021, OpenAI picked up the idea and constructed an even larger data set called GSMK, Great School Math Problem, and used that to fine-tune GPT-3. Another similar work is Sketchpad. They propose a task is the addition of 2 numbers, and they showed great results on fine-tuning, but the prompting accuracy is 0. If we use chain of thought prompting, we just need 1 example and get accuracy 100%. We just follow the natural language rationale by DeepMind. So we can see that using natural language to describe rationales is critical for the success of COT. It's not surprising we can apply COT to any task, like strategy QA, data understanding, sports understanding, all those tasks. We just need to add examples and explanations or rationales. So from empirical studies, we can show actually chain of thought prompting can be on par with SOTA results in the literature. However, we just need 1 or 2 examples for each task, just like usually humans do. So this 100 times or even 1,000 times more data efficient. And also, we have no training and no architecture design. Chain of thought prompting is naturally multilingual. So here, example here, we can see that, and the question in the prompt is in English, and but the testing question is in Chinese, and it works perfectly. And from our paper, actually we show that, and this is particularly useful for low resource languages. We also apply chain of thought prompting to solve big bench hard problems. So here we just compare with human raters. I didn't show the results from machine learning methods because machine learning methods just get 0 accuracy for all the tasks here. So we just use humans as baseline. If you use standard answer only prompting, and human raters can outperform large language models. However, if you use chain of thought prompting, large language models can outperform average human raters with a large margin. And we even can use chain of thought prompting to improve AI safety. Instead of fine-tuning the model to be safe, we can simply teach large language models the safety rules by using chain of thought prompting, just like constitutional AI by Anthropic. Chain of thought prompting works so well, but it still can be greatly improved by self-consistency decoding, another technique developed by my team. So the basic idea is very simple. Instead of using graded solution, we can sample the solution multiple times and then take the most common answer. Look at the panel here. The left panel is the prompt. It contains an exemplar and a question. And then we sample language model multiple times. And if you look at the answer, the common answer here is $18. So we choose $18 as the final correct answer. By the way, I have to emphasize, we choose the most common answer, not most common reasoning paths. You can have multiple different reasoning paths, but all they lead to the same answer. Before I said, okay, if you use COT, we can get results on par with SOTA. We can get results on par with SOTA. But now combining self-consistency with COT, we can crush SOTA results by a large margin. On the GSMK benchmark, so from the OpenAI paper, if you fine-tune GPT-3 with all the training data set, about 7,000 examples, the accuracy will be 33%. If you fine-tune GPT-3 plus a trained verifier means we need additional human labels to rank the solutions. And that way give accuracy 55%. In our approach, we combine chain of thought with PaLM. We get accuracy 58%. We just need 8 exemplars instead of 8,000. And by combining self-consistency, we get accuracy 75%. Average performance of students in the elementary school is 60%. By using PALM2, the newest model, we get actually 92%. Again, we just use the same prompt, same approach. To understand the significance of those numbers, let me quote a paragraph from the OpenAI paper. If you use a fine-tuning approach, if we want to get accuracy 80%, we need to make this data set 100 times larger. That's a typical machine learning thinking. If your model doesn't work well, use more data to train the model. But here, we just use 1,000 fewer data to get solar results. Not just for solving elementary school problems, we can also solve high school math problems. Minerva is a model by fine-tuning PALM with math data. Combining self-consistency and the chain of thought prompting, we can solve 50% problems in the math dataset. Math dataset is actually high school math competition problems. For non-math graduate students, they can solve 40% on average. Why does self-consistency work so well? Marginalization. Think about it. Given the problem, we need to compute the probability of the answer. How to compute? Those reasoning paths are latent variables. To get the full probability, we need to integrate over all reasoning paths. That's called marginalization. To implement marginalization in code, we just need to sample the solution multiple times. It's called Monte Carlo. And then choose the most common answer. From this explanation, we can see that the more samples, the closer to the probabilities of the answers, and thus the better results. Of course, the results will get saturated after more samples. And the number of votes can be used as a model's confidence. And because it approximates the true probability. So here are the results from more tasks. We can see that self-consistency plus chain of thought crushed solar results by a large margin. We just need 1 or 2 examples for each task. By the way, even those examples are not taken from the training set. We just made it by ourselves. So we don't need to use any training set at all. Any questions so far? Okay, let me continue. Yeah, chain of thought prompting and self-consistency work so well, but they still struggle for easy to hard generalization problems. And then we propose least most prompting. So let's look at the last letter concatenation task. Before I said, okay, we can get 100% accuracy, but we have constraint there. If the test cases also contain true words. If you use much longer list, that means use more words to test, for example, 4 words, and then we see significantly performance drop by chain of thought prompting. That's different from human intelligence. To fill the gap, we propose least most prompting. The basic idea is very simple, just like we usually do. If we want to solve a difficult problem, how to solve it? Decompose it to a list of easier sub-problems, and then sequentially solve those sub-problems. That's it. Those sub-problems are ordered with increasing complexities from least to most complex. That's why the name least to most prompting. Actually, least to most prompting is a name from educational psychology. And of course, least to most prompting can be combined with chain of thought prompting and the self-consistency. Here example shows how to use least to most prompting. The only difference is that we first show how to break down this problem. It's top-down breakdown. And how many apples does Anna have, and how many apples do Elsa and Anna have together? And then we solve each sub-problem sequentially. And this is a demonstration example. And the next is a testing question. And use this as a prompt and see what happened. This result generated by language model. See that the model correctly breaks down the problem into 3 sub-problems. And each sub-problem can be easily solved in 1 or 2 steps. So that's how to make easy to hard generalization. Here's another even more amazing example. And we can see that this problem is more complex. And surprisingly, the model decomposed this problem into 8 sub-problems. And again, each sub-problem can be solved in 1 or 2 steps. And so the model can correctly solve them and get a correct answer. It's so much like humans to solve difficult problems, decompose to easy problems and solve them. And not just for math problems, actually, again, just like chain of thought prompting, we can apply this idea to any problems. For example, like say here, can sunlight travel to the deepest part of the Black Sea? We first show the model how to break down this problem and how to solve each sub-problem. And then we ask another problem. Did Aristotle use a laptop? You see here, the large model can break down this problem to when was laptop invented? When did Aristotle live? And did Aristotle use laptop? Perfect. And each sub-problem is perfectly solved. This is another example of common sense reasoning. It's called a chinchillas cold-blooded. Again, the model breaks down this problem perfectly and solve each sub-problem. Actually, in our paper, we make this approach a little bit more advanced. We put this two-mode prompting into 2 stages. The one stage is to decompose questions into easier sub-problems. And for the second stage, we sequentially solve sub-questions. Here you can see that when the model solves the second sub-question, its solution is built on the answer to the first question. That means the answer to the first question is used as a building block. And also, the last question is always the original question. So we don't need another procedure to combine all the answers. Those problems are gradually solved till the final original problem is solved. Now look at the last letter concatenation task. Now it's a length generalization split. Look at the last column. If the list has 12 words, the chain of thought prompting can accuracy 33%, way better than standard prompting, which has an accuracy 0, not surprising. But this two-mode prompting can get accuracy 74%. Of course, I have to see, natural language rationales are not like code, so they are not very accurate. So we didn't get accuracy 100% here. Here's the prompt for list mode prompting on the last letter concatenation task. Actually, we just need 1 exemplar to show how to decompose the lists, and 2 exemplars to show how to solve the problems. And these 2 examples here form a recursion. That's really surprising. That means the model can understand recursion here from step n to step n+1. Here's another challenging benchmark. It's called SCAN. It's called compositional generalization. So we need to convert text to a sequence of actions executed by robots. If you use this two-mode prompting, we get accuracy nearly 100%. And of course, if you look at the literature, the They also got a similar accuracy, but they use about 50,000 examples to train a specialized model. But in our approach, we just use 14 examples. No training, no architecture design. Here's another popular benchmark to test compositional generalization, CVPR. Actually, it's a question answering on knowledge graphs. So we need to convert a text code to get the final answer. In this task, we just use 1% data, crushed solar results. No training, no architecture design. Yeah, just prompting. All those approaches seem really powerful, but interesting, we found out they are easily distracted by irrelevant context. From psychology studies, humans may be easily distracted by irrelevant context. And that means the performance may significantly decrease. And interestingly, we observe something similar in large language models. And look at this example, the same example before, but now we test a new problem with irrelevant context. The irrelevant context here is highlighted as Mario's monthly rent is $10. If given this prompt to tag DaVinci 003, we see the output here, say, okay, the minus $10. Of course, it's wrong, right? Yeah. So they got a wrong answer. How to fix it? The interesting thing is the fixing actually is also simple. We just need to tell large language models to ignore irrelevant context. For this problem, we just need to add a one-line sentence. And then magically, the model generated correct answer. And it knows that Mario's monthly rent is not relevant to this question, so it can be ignored. We created a new data set with irrelevant context. On this benchmark, list most prompting and the chain of prompting dropped around 15 to 20 points. After using this instruction, we got 5 to 10 points back. Okay, I have introduced few-shot prompting. That means to solve a problem, we need to add some examples. And for laymen, they may not want to create any examples. They just want to ask a question and get an answer, right? And that's probably ChatGPT is so popular, or other chatbots, right? And actually, there's no significant gap between few-shot prompting and zero-shot prompting. This gap can be easily filled by instruction tuning. The key idea to instruction tuning is straightforward. Mixing up examples from different tasks, and then using a mixture as the common prompt context for any task. Notice that any task. This is the magic. Any task includes tasks which are not even seen in the context. Of course, if we just put all the examples in the prompt, that would be too many examples to load in the prompt. Usually we have Windows size limitation. But that's not a problem. We can store them in ways by tuning. That's why I call it instruction tuning. In our Flan 2, we fine-tune POM with 1,800 tasks. You can look at the examples here, instruction tuning, chain of thought fine-tuning, all those examples, and put in the large language model. And then we give new task to the model. Let's look at demo here. So this is the email head, and this is a task description. Pass out all the names from this message, and then sort them in alphabetical order by first name, and also add cork to the list. Of course, this is a fake task. We make this fake task to ensure this task is not in our training set. Even it's not on the web, no one would consider such a silly task. Let's see what's the output from a instruction tuned model. Here's the output. You see that all the names are passed out and correctly sorted, and the correctly is in the list. I hope from this example you can see how chatbot works by instruction tuning. That's the principle underlying the chatbots. Now you can use chatbot to ask any questions without any examples. It's zero shot. Why work? Usually people would like to quote Richard Feynman. What I cannot create, I do not understand. But here, we know how to create large language models, but we don't understand why they work. We only have a good observation called emergent properties. That means the model's performance can suddenly jump after a certain scale. Of course, there are many different dimensions about scaling: model size, more tokens, and longer training time. We call them as emergent properties. That means they are discovered, not designed by large language model builders. For example, chain of thought prompting. There's a 2-year time gap between GPT-3 model and the chain of thought prompting. The GPT-3 model was released on 2020, and the chain of thought prompting was discovered in 2022, 2-year time gap. That means every time, if we find new large language model, it's probably the most interesting thing is to discover new emergent properties. Those are not designed by the developers or builders. They need very creative thinking about those properties. And also, I asked my team members how to make parrots intelligent. They said scaling up. That's the answer I expected. We also made a step toward understanding future prompting. We give mathematical proofs, and in context learning can implement stochastic gradient descent and ridge regression. And the transition from SGD to ridge regression as transformer model depths and data noise vary. So you can look at our papers for more details. Now let me give a summary. So I talk about chain of thought prompting, self-consistency leads to most prompting, and instruction tuning. Let me further use a conversation between my daughter and her little brother to illustrate those ideas. They are in the elementary schools, and my daughter asked her little brother, "What's 51 divided by 3? Her little brother thought a while and said, "I don't know." And then my daughter asked, "What's 30 divided by 3? And 10. Was 21 divided by 3? 7. Was 10 plus 7? 17. See, you made it. So I just want to say all these ideas are trivial if large language models are humans, just like my kids. They know all the ideas. Yeah, that's it. Any question?
Thanks so much for Danny's talk, and we have some time for questions, Q&A, and you just feel free to just stand in front of the speaker.
Hi, Danny. Really awesome talk, very inspiring. I have a question. So have you tried these techniques on counterfactual reasoning problems? How well does this work? Do we need some more techniques for counterfactual reasoning tasks? Thanks.
Yeah, great question. And you mean factuality reasoning or?
What if questions?
You mean factuality or text reasoning or something?
Counterfactual, like, what if something happens, right? Like hypothetical questions.
Like a causal reasoning or something?
Yeah.
And so far, based on what I tried, and causal reasoning is quite difficult for large language models. And I tried to figure out what happened there. You can see that for the order questions here, so we just need to predict next words. Actually, it's just a sequential reasoning. We can just get results step by step. But for causal reasonings, we have to think about different hypotheses and go back and forth to verify the hypothesis and see what's the correct answer. Yeah, it's kind of different. So I think I'll be very happy to see if someone can make progress on those problems.
Okay, so does that mean like we need to discover some new techniques to solve it well?
Yes, probably yes. So the new techniques will be could be on different sides. For example, we probably need to pre-train the larger models in some way different, or fine-tune the model in different ways, or need some new prompting techniques.
Okay, thanks.
Hey, thanks, Danny. My question is that given the chain of thoughts examples are all implied in the data source of GPT-3 or those large language models, how come it does not learn the ability properly from auto-regressive learning?
You mean how the abilities from the autoregressive learning?
Yes. Is there any defect in the design of this autoregressive style?
So actually, for the autoregressive learning, the only thing we did is just predict next token. Has nothing to do with reasoning or anything else. So the reasoning ability actually is a surprising discovery. Otherwise, people would already know that after training model, right? Because the GP model was proposed in 2020. At that time, most people just use standard prompting to get results. And the prompting and standard field prompting is much worse than the solar results. And no one cared prompting at that moment until chain of thought prompting came out. After using chain of thought prompting, we can then beat the solar performance. So it's really mysterious. So I hope in the future people can understand what happened during the pre-training stage. Because the pre-training stage, believe me, is so straightforward. Just take all the sentences from the web and predict next token one by one. That's it. There's no magic there. So recently, someone proposed the compressing its intelligence. That means, okay, if we want to really predict all the next token well, then you have to understand semantics and the logics. But no one really can verify that hypothesis.
Okay, so do we have more questions for?
Yeah. I don't think this works. I was curious if you see any kind of analogs from your work in the language domain that would be applicable to like the vision domain. We start to see prompting in the segment anything kinds of models where you're giving it points, and I guess even prompting with text in some cases, but it seems like vision is kind of behind language and the sophistication. And I was wondering if you see any analogs with your work or avenues of research there.
So there are two work in my mind at this moment. One is Flamingo by DeepMind. So it's a model trained with both language and vision. And then you can ask any questions in text. For example, they show an image of neural networks and ask question, and how many layers in the neural network, how many inputs and outputs. And another paper I saw that is called a multimodal chain of thought. They chose visual reasoning tasks, and they also use chain of thought to get the answer. I think that's a paper from Amza.
Hi, Danny. Thank you for the awesome talk. So I got a question about decomposing a task into a series of subtasks you mentioned.
Yeah.
So we know this can be a pretty difficult question or a complex one because you may have like different strategies to generate a series of subtasks. So have you explored that how different ways of generating subtasks or the sequence of your input to the subtask to the large language model can impact the final performance?
Yeah, that's really a great question. So, interestingly, actually, I will tell you. So we invented the digital mode prompting at the same time as chain of thought prompting. At the beginning, when I invented chain of thought prompting, I think it was too simple and make it more advanced, and then we proposed digital mode prompting. But at that time, actually, it's in January 2022. At that time, no model can really support digital mode prompting until GPT 3.5 came out. So that means digital mode prompting actually needs to be supported by more advanced large language models. And even so far, I tried all the models for digital mode prompting. I found out that the decomposition part is really difficult for all the models. So we can say about decomposition actually is a higher level reasoning. So it's a top-down reasoning, it's a top-down. So we need to think about a whole plan before the problem is solved. There's a very high level abstract reasoning, even for humans. And for the GSMK problems, great school math problems, and usually if you say look results by large language models, usually 80%, something like that. However, given the same model, if we manually decompose each subproblem, and the accuracy will be nearly 100%, given a subset I tried. So that means decomposition is really difficult for large language models. And also, the decomposition prompt cannot work across different tasks. For example, if I showed how decomposition works in math word problems, that cannot be applied to common sense reasoning problems. That's why in the common sense reasoning part, I showed different prompt for decomposition. And yeah, so from this study, actually, I'm not sure how large models are smart because they don't know how to decompose. It's much harder. Yeah, they need to be very specific for each task to show how to decompose, and even cannot generalize very well. So we should success on scan and CVPR only because for those problems, the decomposition are simple.
Thank you.
Right, so do we have more questions from the audience? And if not, I think we can thank Danny again for the great talk. Thank you, Danny. Right, so this is the end of our second tutorial, and we will have our third tutorial starting at 10:40. So we'll have a quick short break, and we'll see you soon. Thank you.
So are we all set on Zoom? Everyone can hear on Zoom? Somebody can't hear. Session, and I'm Philip, and I'm going to be presenting this with my PhD student Hyojin over here. So I'll just give the majority of it because she's the expert in this. Okay, so we're going to talk about the overview of this tutorial will be first what do we mean by this word visual prompting? Because I think the talks earlier today were more about prompting vision models via the language inputs. That's what we mean. Okay, about some different models that can be by using with them, but by learning prompts. Okay, so so we're probably mostly familiar in this audience the idea today. Let me just quickly recap how I see that. I think of it as you are steering the behavior of your model, of your language model in this case, by manipulating your system or like and in a language. So you can edit the behavior by changing the context, the language that you provide to that model. And the examples of that property, I can prompt a language model that just predicts the next word to do we trained to do, but it has within the realm of possibilities that's been trained by just giving it examples of translation and asking it to translate. Okay, so should be clear, we've all played hard, whatever. Okay. So visual prompting, what we mean by that is doing the same system. Okay. From Hyojin's, and we're kind of comparing this to fine-tuning. So we're thinking of prompting as a way to adapt the model's behavior. And the model's behavior is by updating the model parameters, the weights and biases of a neural net pattern. Okay, so if I have some classification task, want to recognize this flower, and I want to up model to work better on maybe nighttime photos of flowers and trained on daytime photos, I can fine tune it, and there's a lot of different algorithms for tuning models to achieve better performance. Okay, so prompting performance via input space manipulations. So the yellow is the adapted parameters, and the yellow is the adapted data. Hyojin will talk in a lot more detail about exactly how this optimize the input to achieve a new performance or a new kind of classification ability. Model fine-tuning, but not on parameter space, on data space. And this has started very kind of popular when beyond editing pixels, but can also prompt the model with other types. See examples of this segment anything model that came out recently where the visual data that you are changing the pixels, but so what I want the model to do, I will that bounding box. And here's another work that Hyojin will talk more about from Alyosha Epra. Prompt is, it's like an in-context example. It's an example in pixels of the desired input-output behavior. And then it's just trying to fill in the gap. We'll hear a little bit more about those systems in just a bit, but I want to now comment on why I think prompting is really interesting, right? We have popular ones like LoRa or efficient methods. Those are wonderful. What is interesting about this? And to me, it's all about the input space. It's editing model the input space as opposed to the parameters. It's a whole bunch of new And maybe the main one, the most important, is kind of human compatibility. The inputs and outputs of models. They don't think in terms of model parameters. So inputs are usually or often, right? So the images, the inputs to language systems, visualize information. Okay, so if you can edit a model by the inputs, then type of representation, and additionally, this can work with. You want to edit OpenAI. Of course, you don't have access to the model. How do you do it? You can do it by input space manipulation, because the user always controls the input, or generally the user, if they're to that system, they might not uses as inputs or what is out the inputs. So this prompting is this interface to model editing that you can use, that you can understand, and that's what I think is exciting about it. Okay, so of course this is not a new idea by any means. Prompting has been around for many decades. It didn't go under that name in the past. Here's a really great analogies. So from Aaron Kurtzman and colleagues, this is about there's an analogy between this stuff, prompting way of thinking about this. Okay, here in the modern lingo, and here I have a query, and it's saying, okay, given that example of behavior, I'm prompting the system to do this, then I will perform that operation on the query. Okay, so this idea of steering an computer graphics. I think SIGGRAPH and these conferences, they have names like interactive systems or computer graphics, interactive media, stuff like that. Okay, so graphs that respond to user input, I think is really prompting, and that's the whole. Okay, here's that we did, which you could read. You have an image, you want to colorize it, and the user will with that of like in segment anything, you can click points, and of course there's a lot of other old segmentation algorithms. Here to control the model speed. Okay. So there's a long history that is that most of those older systems were really trained to just do kind of one thing. Conditional generative models, models that are conditioned on respond to the types of inputs that they. And I think prompting is much more about adapting a system. It might be unexpected, explicitly trained to do. About adapting models they weren't necessarily pre-trained to do. And I think even if I have these conditional inputs, I have I'm a graphics researcher, and I'm making systems that input controls. There's been that much work. I mean, there are fields where there hasn't been that much optimize those controls, and the prompting a lot. That's super interesting too. Okay, so one more thing, prompting and input space is models in this fashion. You get flexible integration, not just with humans who also operate over images and text, but over other models, because most of the models that are put out operating over images, text, and other types of input formats, data formats. So here are two examples of how you can kind of hook models and prompt the input image and object detector that will output another type of data representation that could be for and bounding boxes, right? And now a user could just take those bounding boxes, become the prompts, because that kind of representation is like an input space manipulation. We think of those as control prompts, put those into segment anything, which has been to deal with that kind of input, and it can combine these two models. Kyojin will give more examples. I'll just give one more before passing it off to her. So segment anything has caused a lot of excitement here. So we can apply segment anything to get the mask of the dog on the bench. Put that into take a mask and text as input and output, glue the system together to output this style transferred masked region. So that's the overview of what I'm excited about, seeing how I like to look at it. I think we're going to see a lot more technical detail now from Kyojin.
In Vision, I will demonstrate 3 cases where we formulate prompting as a connected to empty task, segmentation task, and generation task. One of the earliest examples is visual prompting by image painting. Conventionally, we train separate models for each visual task, but the motivation of this paper is when you train a single general model that can form a wide variety of visual tasks without additional fine-tuning. So they simply pose different images problem. So they give, like in context learning and language, they give demonstration, and this describes the visual task without and they concatenate that with the image to create this, and it is given as input to the implementing model, and the model and by different context examples, this will form different vision tasks. And so how visual does not look at all like the natural images that we usually use for training sets. So to reduce this domain gap, a computer figures from archive, in the in painting model using MAUPQ again, able although still on traditional fine-tuning, this was a great proof of concept of visual prompting an painting model that was trained on language. And I think the community is so excited right now about visual prompting is demonstrated by segment anything, which is able to put distributions and tasks. So the goal of this paper is to build a foundation model for each segmentation. And how they do that is to design the model. So it's to be promptable so that you can transfer zero shot to new image distribution. So to design this model, there are three components. First is what task will enable zero shot generalization. Second, what is the picture? And then third, what for this question they define a promptable segmentation task. What this so that specifies what to segment. So the boxes or masks alongside with the segmentation model generate response prompts. So even when a prompt is ambiguous, the out should be reasonable for at least one object. If there is dot on this image, it corresponds to the entire ball, or it could correspond to just the dot dot, or it could only correspond to the label on the dot dot. So the model is designed to valid masks. For the second question, what is the responding model architecture? So they enable three features to support real-time ambiguity aware. So for interactive use, they actually couple the model to a one-time heavyweight image encoder, which is an MAE pre-trained vision transformer, and a very lightweight prompt encoder and a mask decoder that can just run in a few milliseconds for each prompt. So by doing it this way, the same prompts so that it and they allow flexible prompts, so they allow multiple types of visual prompts such as points, bounces, where the user interactively play with the model, but show cues to the model of what they want, what they desire to segment. And then finally, the model is designed to be ambiguity aware, so it predicts multiple output masks for a single prompt, and the default is sort of three masks. Part of this task, design a very large-scale data set consisting of 11 million and 1.1 billion masks. So how they create based on annotating and training the model. So stages. In the first stage, it is model-assisted manual annotation stage. So at this point, they hire professional annotators, and they give them a very to generate very high-quality annotations, and then train the first batch model. And then in the second stage, they actually use the pre-trained model, and they give a mixed supervision of the predicted masks and the assistive tools to automate the labeling stage. And finally, it's fully automatic. So at this point, the model can accept prompts. So it gives multiple prompts to the image and to the model, and the model generates multiple plausible valid masks, and they only filter very confident masks, use that as training data to train the final version of the model. So finally, this trained model really has an amazing zero-shot transfer to image distributions and tasks. But I think what gets me more exciting is its flexible integration ability. So what it can do is you can combine it with boxes and just give those predictions as a visual prompt, and instantly user gazes from a ARB as point and point prompts to segment anything that the uses, or it can be combined with the 3D mesh generation or even video processing. endowing flexible ability to a foundation model dramatically because it can be incorporated as part of a more complex system. The third example that I would give is creating a promptable image generation model. One example is Gligan, but I think people might be more familiar with ControlNet. Both of them are very similar methods. You should also look into it. So to create a promptable image generation method, usually a pre-trained text-to-image generation model like Stable Diffusion or DALL-E can only control image generation through a text prompt. A lot of people who has done this is very laborsome and it's very annoying because you never can precisely find the text prompt that generates the desired output. So instead, Gligan wants to increase its controllability by adding more precise forms of visual prompts that can guide generation so that you can generate more precise images that the user desires. So the goal of Gligan is to enable new conditional input modalities such as key points, depth map, normal map, or semantic map to existing pre-trained diffusion models. How they do so is to create a grounding token alongside with the text prompt that a model receives. So how they define this grounding token is first they introduce a semantic information, which could be text or even example images, alongside with facial configurations in box that corresponds to. And then we and the combined is given as into the once you obtain this grounding token is introduced to the model, but the original layers remain entirely frozen. You do not modify any parts of the model. Instead, insert a gated self process gated self-attention layer to allow the new conditional information. To build the combination of open source data sets alongside with semantic maps for the open source data sets. And once the model also, because it is comfortable, they also ways of combining with other systems, such as you can get general bounding boxes from grounding. Use those bounding boxes as the prompt to where prompt, and it's sometimes better than using models like instruct pix to pix because sometimes the method doesn't precisely dog that I want to transform. So instead of giving a prompt like precisely find the bounding box for the dog and then generate the cat. Three examples of how to create a vision foundation model that can that has the visual prompting ability. But I also want to elaborate on visual prompt learning methods as a parameter efficient fine-tuning method. So the notion of prefix tuning or prompt tuning is a very popular framework in language where you can essentially treat the prompt as a continuous vector that you can learn. So for instance, rather than having training a separate transformer for each downstream task, what they do is they own, which is a continuous vector, and they just prepend that to the input tokens. So just changing this continuous vector, the same language model is able to perform different downstream tasks. You can do this in vision tasks as well, and for vision foundation models. So we show two cases where a vision prompt can be learned via pixels embedding space. To adversarial reprogramming, which was first proposed as a adversarial attack where you learn input perturbation, and by adding that input perturbation to every image, the model, the pixels reprograms the target model to perform a task. Although the performance not is able to prepare the model to perform a task that was not desired by the actual user. We take a different approach and actually use those pixels to increase performance of a task or adapt a same model to a different task. So we show that a visual prompt can actually be learned in pixel space. So for instance, we have this visual prompt, which looks like input perturbation, but just by adding that input perturbation to every image, you can tell a model to classify dog species or a bunch of other tasks. So essentially, a prompt is a continuous task-specific vector. So this single prompt can be added to every image to perform the task that is provided. So how do we learn this interpretation? It's actually very simple. So we try our method on a multimodal model like CLIP and traditional vision model. So to prompt a prompt with CLIP, we first need to define an input transformation and output transformation. For the input transformation, we learn the visual prompt defined by pixels. And for output transformations, it is done by text prompting, which is the default setting for CLIP. And then the entire CLIP model remains frozen, and we just propagate through the model and learn the soft prompt, which is defined in. Similarly, we define input transformation as a pixel transformation, and for output transformation, kind of the hard coding mapping where would refer to a dog class and the index 2 class. And we similarly just fix the entire parameters of the image for the unlock propagate to obtain the pixel prompt that we desire. And then during inference, once we obtain this single visual prompt, we add that to every test image. So it's just a single pixel perturbation for the entire task. And then the model is able to perform flower classification just by adding this pixel perturbation. We find that we try this method across various vision foundation models and see that CLIP is particularly effective for pixel prompting. And it is very effective for reducing the distribution gap. So tasks that CLIP was originally very bad at, and for Eurostat, the performance increases dramatically by learning a visual prompt. Then we can also learn a visual prompt in the embedding space of a transformer. So in this method, what they did is they learned a soft prompt in the embedding space of a transformer alongside with the linear head of the transformer, and that is defined as the visual prompt. And they learn this single embedding for an entire task. And this actually outperforms full fine-tuning, which is a very surprising result, because even though you scale the entire language, prompt tuning never really excelled full fine-tuning. Whereas for visual prompt tuning, it showcased, for example, where you can actually, by only tuning a subset of the parameters, you can actually excel the performance of tuning the entire parameters of a transformer. But actually, this is still an open question of what is a good recipe for visual prompting to work very well, because you can't actually switch the model architecture to a training base, then actually the model does not outperform full fine-tuning. So it is still an open question of what is the best setting where the prompt tuning excels full fine-tuning. So there are several takeaway messages regarding the entire prompt. First, we see that visual prompting allows adaptation of foundation models in input space, and we find that input space is the most interesting part for prompting because is a universal interface not only for humans but also for models, such as shown in the segment anything example, where you can combine multiple foundation models by making the models comparable. And it essentially increases the usability of the model for more flexible interface, for more complex systems that we want to build. As shown in the previous examples, how to increase promptability of a model is still an open challenge, and we still don't know the precise recipe to increase the promptability of any foundation model. And we also finally show an example where learning a prompt can be treated as a parameter efficient fine-tuning method, such as LoRa, and it sometimes outperforms full fine-tuning, especially for visual tasks. This is the end of the talk. Thank you for remaining time as the questions. Thank you.
Any question from audience? You can just speak. Yeah.
Hi. For the talk, I have one question regarding segment training. You showed us an example of using grounding before segmenting it to do semantic segmentation or recent segmentation, for instance. But I think that concatenating these two models of grounding we get the bounding boxes as prompts that we give to have this class agnostic class. My question is, how can we, for example, what do you think about using the representations of the image encoder, segmenting it, to do directly semantic segmentation? Because I think that since if is not able to detect the objects, it won't be segmented by segmentation. So, what do you think about using this feature representation image encoder, since it has been trained on billions of images, billions of masks, or as a pre-trained model that we can fine-tune for
like semantic.
So I think semantic segmentation by default is designed to produce masks that uses the features and these prompts just act as an additional information to aid the prediction. So actually we are using and the additional bounding boxes that just literally is as a prompt that helps prediction. But if you run any agent yourself, it already has an amazing semantic segmentation ability. But I think the example that you're referring to can be referred to. There's also a paper called segment everything everywhere all at once. And I think that paper essentially is doing what you're saying, where the model is fully tuned to output roughly where they want. So I think you should.
Thank you very much.
Yeah. Thank you very much.
Thanks for a really nice talk. So in that area, like now we have a lot of so given the new with the visual prompting, so can we actually design a new training framework for the visual model? So for in NLP domain, like now some language models are trained to understand the fusion prompts. So how to better handle the fusion. So do you have any idea like what would be the model or the training objective? Yeah, what would be the next steps to further improve for the models that better understand the visual prompts?
I think there are multiple ways of doing this. I think right now people are more excited about creating multimodal models like GPT for adding vision prompts. So usually they provide natural language instructions alongside with the images, and that actually helps the model understand the examples better because you're just giving more cues to understand them. And secondly, I think definitely it depends on the trait scale and diversity of the training data. And I think diversity matters a lot because if you just scale it, there are multiple cases where your amazing vision foundation models trained on billions and billions of data sets, but they just don't become viral because their performance is is actually lower than a 2 billion. They're like a 500 billion model is lower, has lower performance than a 2 billion model. So I think creating a really good training set that excels not in terms of scale but also diversity is very, very important.
I have a low level question. So, there could be multiple ways to combine this. Like, can swap the orders. Like, do you think like concatenation or adding independent spaces? Do you think which one is important?
I think the best is to make it as flexible as possible. For instance, I feel like the usability of Flamingo is lower than, I don't know, like the GPT-4, just because it's precisely trained to have inputs in input output format. So it cannot process more complex context because its input format was fixed that way. So I think making the input formats as diverse as possible during pre-training is very important. Very important. Yes.
For sharing, and I have some questions about your work on video. And I read that paper, and you're also studying the prompt size, right?
Mm-hmm.
And I'm wondering, when you scale the prompt size, will you also scale the image so that they will not overlap?
Not really. I think what's interesting about the prompt size is that you don't want it to be like if you increase the size too much at a certain point, the performance actually decreases.
Yeah,
and
but I think it's clearly because you
but we can
overlap on the thing.
Yeah, so we only showcased one example of how you can add the prompt, but you can actually prepend it as a border rather than overlapping on the image. But I think having it's the similar there's a similar observation in language as well. We still don't know why, but increasing the prompt size too much at a certain point decreases the performance. And we saw similar observations.
Yeah. Can I add one thing? Sorry. So the overlap, I think that's a common question. So I just wanted to say, the pixels you're adding are optimized to optimize performance. So if the best thing to do is not to corrupt the image and really showcase a lot of it, it should learn to do that. So I don't think there's like a fundamental reason why having adding a pixel mask, which is the full image size, would not work. That can work too.
Okay. Yeah, I want also studying on this work. And another question is, did you find what kind of downstream test is more useful for using visual prompt?
So what we've been observing is that if the image that the model sees is more OOD to its pre-trained data set, you get more performance gain from visual prompt training rather than language prompt training. So it's very essentially if you're just minimizing the distribution gap by adding these pixels. So if there's a lot of distribution in the pixel space, this will help a lot.
And also, will you constrain the prompt parameter to like 0 to 1?
So we observed that if you minimize the restraints, better performance. Yeah, minimize the constraint. So if you make it like imperceptible, like adversarial examples, then the performance decreases.
And the next question is on the level output. It also needs to do some labeling.
Yes.
I've read some papers on frequency labeling. So it's very level. You study some of choosing the labeling to make the visual prompt more higher.
We didn't specifically try those two methods, but what we observed is that rather than doing hard-coded mapping, if you just tune the last linear layer, then the performance increases dramatically. Yeah. Tuning is the best.
Okay, thank you for your talk. So I have a question about the visual prompt training right after. So I think you mentioned in your takeaway page that even if we have those code prompts, but actually I think visual prompt training comes differently with like the text prompt and the
the building blocks prompts in SAM, because in my opinion, certain more performs more like the path version line of work, which means it kind of introduces more like learnable parameters, and then try to perform a parameter division term. So do you think this kind of learnable soft prompts perform similarly with the readable prompts like the one that's in text, or they should like complementary, they should?
If you want to make your model excel at a specific distribution, then I think prompt tuning works better. But if you want your model to excel at numerous unseen distributions, that I think prompt tuning, like with boxes and sort of data.
I think in this kind of readable prompts might be more general, different kinds of different distributions. So general is better, but for very specific distribution, like very single case, it might be better to use BPT style. And also
Yes, because you're precisely optimizing the prompt to find the best working prompt for that particular distribution. So in that sense, it's maybe way more useful than having to find the optimal points of bounding boxes yourself.
Thank you.
Yeah. Okay. Just one more comment on that. So yeah, I also agree that I think if you're doing this in embedding space, it's not really clear if the right way of thinking of that is prompting or more parameter efficient tuning. But maybe one way of categorizing things is there's 3 important variables in making the system work. One is the data X, 2 is the embeddings Z, like transformations of the data, and 3 is the parameters theta. And you can adapt or tune any of them. And the kind of prompting I'm most excited about is adapting the data X, because then it has this data interface and it integrates with other models. Fine-tuning and parameter efficient tuning is all about adapting theta. But then there's this other thing, adapting Z, like the activations or latent variables. And visual prompt tuning does that, but I don't quite know what to call that. I think it's a different category to me.
Yeah, hello.
First of all, for the next talk. So we have seen that conditioning text image models of visual prompts helps. But imagine you want to overcomplicate this task. Imagine you want to do like text to video. Specifically, imagine you want to model this tool. And defining this in a text prompt is what do you think about adding some visual prompts? Do you think that maybe conditioning this kind of model on a simulator?
Awesome. So I think what you just said, I think can be achieved by combining segment anything and an optical generation model, where you essentially are creating these visual prompts for the 3D generation model, but you do that by segmenting the image or creating bounding boxes, and that visual prompt is a much better gives you much better controllability of precisely finding which 3D generation you want to generate or which part of the image you want to modify. Or did you want something other than this?
I mean, just
yeah, I think right now it is achieved by combining different vision foundation models and increase the ability to connect different systems by adding these promptability to the model. Because I think it's very hard for a single model to perform everything. So for segmentation and segment anything, we just train a really good foundation model that excels at prompting and then excels at segmenting, and then you combine that to a 3D model that can receive masks or bounding boxes.
Hi, so I have a question about currently, I think we still don't have very powerful vision language models, because before I think the video I think like the question is like RH has played a very key role in getting large language models to follow instructions, right? And then also RHF is relevant for visual function?
So there are works where they do visual instruction tuning, where they create data sets, I think, combined for a couple of vision foundation models, and they just generate multiple multimodal prompts that combine images and language.
You mean like or
Yeah,
Lava?
yeah, or Lava, and I think that's one way to achieve it.
I believe they put the whole image, not sure how well that works for visual prompting where you have points or boxes.
I'm sorry, what's the goal that you're trying to achieve?
Oh, so the goal is let's say out loud, right? So have anybody tried visual prompting for that kind of models?
No, currently it's only applied to vision models. Or I think clip that we tried. But for the more recent large scale models, it hasn't been applied yet.
I think these techniques apply for.
What do you mean by this?
For example, you get a box, right, and then you can say, classify this flower.
Well, I think that definitely. I think right now, I think the key to creating a very powerful foundation model is essentially creating a really good multimodal prompts, endowing the ability to understand very complex multimodal prompts. Then you'll have a very powerful foundation model. And I think the key challenge right now is how you create a very high quality, large scale data set that has multimodal to image text. But you're right, you can definitely combine prompt tuning or prompt to create those data sets.
So maybe, yeah, one last question.
Yeah, thanks for the great talk. So I have a question about the initialization of visual prompts. So if I remember correctly, in prefix tuning, they find that if you randomly initialize the soft prompts, training can become unstable versus if you initialize the prompts with semantic meanings or related to the task, some common vocabulary, the training stability can improve a lot. So I'm wondering if you have any insights about how to initialize visual prompts.
We also tried a similar approach, but for us, random initialization worked best. But I think it all depends on the vision foundation model that you want to apply to. So the results may be different for more models.
Gotcha. Yeah, you're not.
One last question.
Hi, thank you for your nice talk. I have one question. As we have seen that in prompting, we adopt a model using a pixel space fine tuning. So at the same time, the another variant is full fine tuning, which we adopt using the weight space by changing the layers. So instead of showing this as an alternative method to adopting model, have you ever tried exploring using it as a complementary to fine tuning, so that in a single pipeline we have prompts which are learned as well as some part of the model which is learned? Are they presenting same? Are they learning same type of representation, or they are just doing the same job?
When we were writing this paper, we tried to compare it with full fine tuning, but not necessarily combining them. We found that combining with linear probes does increase the performance dramatically and sometimes sell full fine tuning, but we never tried doing visual prompting first and then do full fine tuning. But it's an interesting question. Yeah.
Okay, so let's say.
can also unmute yourself.
Oh, yeah. About that. Thank you. Okay, so my name is Sarah Pratt. I'm a third-year PhD student at the University of Washington, and I'm going to be talking about my work on prompt generation for zero-shot image classification. So before I dive into my work, I'm going to ask you all to participate in some clip-style image classification. That is, I will give you several captions and ask you all to please match the image with the correct one. So here are three captions: a photo of a Saluki, a photo of a Vizsla, and a photo of an Abyssinian hound. These are all dog breeds from ImageNet. So just by show of hands, who thinks this is a Saluki? Okay, who thinks this is a Vizsla? And a Abyssinian hound? Okay, that seems to be the winner. Okay, great. So now I'm going to give you three different captions. All right. The easiest way to identify a Saluki is by its iconic long silky ears. A Vizsla is a short-haired red-brown hunting dog, and the Abyssinian hound is a slender, elegant dog with large bat-like ears. So again, show of hands, who thinks this is a Saluki? Okay, a few more hands. A Vizsla and an Abyssinian hound. Okay, definitely fewer there. Yeah, so the correct answer is a Saluki. So what I hope to have demonstrated to you all, and what many speakers before me have demonstrated as well, is that text is a powerful tool in identifying visual features, especially in the zero-shot setting. Towards this end, I will be presenting on our method of using customized prompts via language models to generate descriptive captions of categories, just like the ones seen here, which are all LLM generated, in order to improve zero-shot image classification. Before I fully describe this method, I want to go into a little more detail about the standard method of zero-shot image classification for models like CLIP. As has previously been mentioned, these models are trained to encode text and images, and then provide a severity score of these encodings based on how likely it is that a certain piece of text is a caption of that image. To use CLIP for image classification, the authors of the original CLIP paper proposed a method in which they handwrite prompt templates, which are designed to look like image captions, and then complete each of these templates with the names of the categories in the data set. These captions, as well as the images, are encoded, and then the image is categorized based on which caption encoding most closely matches the image encoding. This approach to image classification comes with a few challenges. The first challenge I've already demonstrated, which is that prompt templates are not able to capture any visual details about the categories. And these visual descriptions can often be very valuable for classification. With the standard approach of generic prompt templates, the only information which is specific to the category is the category name. The second challenge is actually in writing the prompt templates. So here I'm only showing a single prompt template, which is a photo of a blank. However, in practice, the standard approach is to ensemble many different prompt templates. As an example, here are all the prompt templates used in the original clip paper for ImageNet. And handwriting all these templates for a single data set is a time-consuming process. So a bad photo of a blank, a photo of many blank, and you'd insert that with the category name and ensemble embeddings of all of these different templates. The final challenge to this approach is that we often need to know information about the data distribution in order to write effective prompt templates. As an example, here are the prompt templates from ImageNet again, and here are two specific prompt templates. One good template if you have a photo of a real version of the object, and one is a good template if you have a toy version. In ImageNet, we do see categories with real and toy versions of objects. However, this might not be true for all data sets, and therefore these templates might not be as effective for all data sets. So in summary, we want a method for creating these captions that addresses these challenges. In particular, we want our captions to contain specific visual information while requiring fewer handwritten sentences and to not use prior knowledge about the data distribution. And we want all these things while still maintaining or increasing the accuracy of the model. As I've already mentioned, we're going to use an LLM to accomplish this. So instead of the standard setup where we use prompt templates, we are simply going to ask an LLM to provide a description or multiple descriptions of our image categories. So what does a platypus look like, or what does a whatever look like? And it will output some description. For example, a platypus looks like a beaver with a duck's bill. And we're just going to replace our handwritten templates with the output of our LLM. We call this method customized prompts via language models, or couple for short. And as you can see, when we ask an LLM to describe our ImageNet categories, we get rich visual descriptions that contain much more information than those original templates. Now, one drawback of this method, admittedly, is we still have to do a little bit of prompt engineering. We are now automatically generating the prompts which we feed into Clip as the image captions, which we call image prompts. But we still need to construct the prompts to query the LLM, which we call LLM prompts. So the first goal when we began this project was we wanted to improve accuracy with significantly fewer human written prompts than the standard approach. So let's look at the prompts used in the standard approach for a small selection of data sets. The standard clip method uses 80 prompts for ImageNet, which I showed previously, 28 for Kinetic 700, which is an action recognition data set. And then for some data sets, they only use a few. So for this aircrafts data set, they actually only use 2. And here's the accuracy when using standard prompts across 15 different benchmarks. So in the top row, we show the accuracy. And then in the second row, number HW is the number of handwritten prompts that are needed for the prompts for that specific data set. So some of them are a lot, like 80 or 48 or 28, and some of them are fewer. And here's sort of the summary of that. So we have an average accuracy of 73.43 across these 15 different benchmarks, and a total of 175 unique handwritten prompts. And note, we want to be in the top left corner of this plot because we want the highest possible accuracy with the lowest possible effort. And here are the prompts we came up with in order to prompt the LLM to generate descriptions. So we have 5 for ImageNet, 4 for Kinetic 700, and 2 for aircrafts. And we did this for the 15 different data sets, and here are our results. We see a higher accuracy on every single data set with more than 1 percentage point gains on ImageNet, 6 on describable textures, and 4 on Sun, which is a scene classification data set. And we can see now we have significantly higher accuracy on average, increasing 1.4 percentage points on average across all the data sets, while also requiring way fewer handwritten prompts overall. One of the reasons we were able to accomplish this is because the number of prompts used in the CLIP model, which we call image prompts, are no longer linearly proportional to the number of sentences a person has to write. So for ImageNet, in the standard method, if you want additional descriptions entered into CLIP, a person has to handwrite that. So a bad photo of a blank, it's just exactly 1-to-1 with the number of sentences a person has to write. But now that's no longer true. So you could write one or these 5 different questions, and then you could query the LLM for multiple different responses with the same amount of human effort overall. And we find that this is actually very helpful. So here's a figure of the total number of image prompts versus accuracy, keeping the number of human written prompts to the LLM constant. So here we're using those same 5 questions I showed previously, and you can see the accuracy when we generate 1 response per question. So 5 responses is well below 74%. But when we generate 5 responses per question, so 25 image prompts overall, it jumps to above 76%. So this is very encouraging because it means that we can take advantage of the LLM's ability to rapidly generate multiple responses to the same question in order to improve overall classification accuracy. At this point, we were pleased to have improved on all these data sets. However, we still weren't completely satisfied with the setup, as it still requires some prompt engineering for each data set. So we additionally created the couple base setting, which uses these same 3 prompts across every single data set. We found that this beats the baseline on all but 2 data sets. And here's couple base in relation to couple full and the standard setting. So essentially, our goal was to have higher accuracy with lower effort, and we present these 2 settings with different balances of this trade-off. So if you don't want to do any prompt engineering at all, you can use couple base, which is slightly lower accuracy than couple full, but still on average higher than the baseline, even though the baseline is prompt engineering a different set of prompts for every single data set. And if you just want to maximize your accuracy, you can do some prompt tuning for the different data sets, although much less than the baseline method. Overall, though, both of these settings have higher average accuracy with lower average effort than the standard method of prompting. Additionally, we did some investigation into why couple descriptions lead to higher accuracy. When we look at descriptions, we're able to use the text to understand which regions of the image are important for making our classification. We wanted to see if the model was using text in a similar way. To do this, we employed Shapley values, a method that is commonly used in interpretable AI to understand what features are contributing to an outcome. Specifically, we selected an image and then classified it between 2 very similar categories, once while using the standard set of prompts and once while using couple prompts. We then examined which region of the image contributed to a higher accuracy for each class. As you can see with the standard prompts, the important regions for the image of the promontory class are a bit of the water, but much more highly on the tip of the rock formation. For cliff class, the important regions are on the rock face, the sky, and the foreground. However, when we look at the Shapley values when using couple prompts, we see a very strong value on the water region for the promontory class, which makes sense as water is one of the most frequently mentioned words in descriptions of a promontory. For cliff, we see the importance is centered very heavily on the rock face. Additionally, we note that for this image, the standard approach produces an incorrect classification while it is correctly classified when using couple prompts. We see a similar case when classifying between 2 different types of frogs. For standard prompts, we see a small amount of importance on various regions of the frog for tree frog versus tailed frog. However, when we look at the important regions when using couple prompts, there is heavy importance on the eye, which again is frequently mentioned in the description. And again, we see that this image is correctly classified with couple prompts, but not with standard prompts. And note, while these visualizations are qualitative, you can find quantitative results of this phenomenon in our paper. There are a few other works that I want to mention before I wrap up. Firstly, one advantage of this method is it is additive with other methods. So for example, a group of researchers recently trained an open source version of CLIP to achieve an 80.1% zero-shot ImageNet accuracy. And when they also included couple prompts, they gained an additional 0.2%. Additionally, some of my colleagues from my lab recently wrote a soon-to-be released paper where they adjust the weights of CLIP in a few-shot way to the current downstream task. Again, they found that the accuracy gains from couple were additive to their own. Finally, I want to mention several works that came out around the same time as this one that demonstrate how the same idea can be useful for more interpretable models. The first is from a lab at Columbia by Menon et al., which uses an LLM to generate descriptions of classes in the form of a list of attributes. They are then able to see how much the image matches with the text embeddings corresponding to each of these attributes. The second is this work by Yang et al. From UPenn, in which the authors use an LLM to generate concepts that may describe the classes of interest, and then map images to a score for each of these concepts before using these scores to classify the image. This forces these black box latent representations to go through an interpretable language-based bottleneck before ultimately outputting a prediction. In conclusion, models like CLIP are sometimes viewed as a method to achieve high accuracy on tasks like ImageNet without the labor-intensive process of human annotators. However, working with open vocabulary models and reading about the exciting work by other researchers has shown me that these models are shifting the relationship between language and vision, enabling things that are not possible even with the best hand-annotated labeled datasets. Our vocabulary and with these models expands from 1,000 or N concepts to every possible word. We can use language in new ways to interpret novel concepts, improve accuracy on previously studied tasks, and probe models to understand what is leading to their predictions in a human interpretable way. Finally, I want to thank my co-authors for their invaluable contributions to this project, and thank you all for your time. Oh yeah, if there's any, I can take all.
Yeah, so any questions you can.
Yeah. So can you relate this work to this talk we heard about chain of thoughts, and we heard about chain of thought in language processing? Is it adding chain of thought into visual language and image understanding?
Yeah, you could think about it in a similar way of you're breaking down what you're looking for of instead of looking for like this whole entire concept, the text breaks it down into like its different components. And now you're trying to classify the image in terms of like, does it match, you know, the duckbill and the like beaver-like body, as opposed to, does it just match this entire concept?
Can you take it one step further? So in chain of thought, you break the task into subtasks. In here, you know to break the identification, classification into attributes of the image. Can you make the model show these attributes rather than using this SHAP method to find this attribute from the back door? Can you ask the models in the forward task to give you these attributes?
I see. Yeah, so that's, I think, yeah, there's a lot more work that can be done in that. It's a little similar to the paper at Columbia, which generated each of these attributes and matched it one by one. That one has greater ability to interpret, but a lower accuracy. But I think that there should be a way to be able to use that to get a higher accuracy overall. So I think there's just like still more work to be done in the space.
Thank you very much.
And maybe also a quick question. Thanks for the talk. Did you tune the large language model inputs in any way? Or was this kind of like you tried a couple things out and then what ended up working?
Yeah. So just sort of like based off of my like experience, like for for ImageNet, like those were sort of like the first 5 ones I've tried. I actually think there's more accuracy that can be gained from tuning it a little bit more. And then since I was sort of testing it on the validation set, I also tested it on the ImageNet V2 data set, which I like didn't do any tuning on and saw the same gains. So
do you have any idea how you would try to tune large language model inputs without getting to that model again?
I'm not sure. Yeah, because like the COOP method obviously is sort of how you could do that automatically. But just without, trial and error between those two methods, I'm not sure. Yeah.
Thank you.
Yeah.
Okay, so let's thank Sarah again.
Okay, cool. Hey everyone, I'm Ludwig. Thanks a lot for staying, and sorry that we are going a little bit over time. I'll be quick. And to be honest, this talk isn't really about prompting anyway. So if you're only here for the prompting, you can leave now. But okay, let's get started. What am I actually going to talk about? So I'm going to talk about fine-tuning, because sort of like even in 2023, the best models still come out of a two-step process, right? We first pre-train a large model on a lot of data from the web, like Clip, GPT, Flamingo, and so on. And then the model is good, but not quite good enough often with what we want to do exactly. So what we do in step 2 is we fine-tune it on a small amount of task-specific data, like instruction following data, or like a specific downstream image distribution we're interested in. And what I want to tell you about is some lessons we have learned over the past couple of years. What is the best way to fine-tune a large pre-trained model? And the focus specifically is going to be on out-of-distribution robustness, right? This is a very important topic. We have made tons of progress over the past 10 years in machine learning, computer vision, and so on. But when we take these research advances from our benchmarks into the real world, it's often quite hard to make them work reliably. I think the prime example of that, so self-driving cars, there were many predictions a decade ago, around by 2020, we'll have lots of self-driving cars, and there's progress, but it's much harder than we thought. And the same is true in many other areas. Often sort of like making these computer vision machine learning tools reliable is a really hard problem. And this is still true, obviously, in 2023 with chatbots, really amazing tools, but hard to get to work reliably. Cool. So what are we going to do in order to make machine learning more reliable? And sort of as a guiding example and case study today, we are going to look at robustness on ImageNet, because this is one of those data sets where the community has pushed really hard for a decade and we've seen amazing progress. But if you take these models out into the real world, they are still not as perfect, they're still not as reliable as the human visual system. And one way that people have made this more precise over the past few years is by building new out-of-distribution test sets for ImageNet. So like here, probably the four most widely used example, ImageNet v2, ObjectNet, ImageNet Sketch, ImageNet R. The exact details of these don't matter right now. The idea with all of these is, let's build a test set with the same classes as ImageNet. So we can use an ImageNet classifier right away in a zero-shot manner, but we are going to change some things about the distribution of those images. Maybe we'll change the mtalk annotation process, or we'll use sketches instead of real images, and so on. Cool. So just to give you an overview now, what is state of the art on these out-of-distribution test sets, let's look at the results of a large benchmark evaluation study we did a couple years ago. And this is sort of like a really important plot for the rest of the talk. So we'll go through this step by step. So on the x-axis of this plot, we just put standard ImageNet accuracy. And then on the y-axis, we put accuracy under a distribution shift. As a first example here, ImageNet v2. And then I've put 80 different models on this plot, from the seminal AlexNet paper over VGG, ResNet, DenseNet, and so on, to the state-of-the-art model at the time, which was an efficient v7. Okay, and there are a couple of things to note with this plot. One is that all of these models suffer a noticeable performance drop. So the dashed line is y equals x. All of the models are around 10 to 15% below the dashed line. Okay. The other thing that's nice about this plot, all of these models, although they have quite different architectures, training algorithms, and so on, all of these models follow a very precise linear trend. And this is going to be useful because we can use this as a baseline. So specifically, if you give me a new ImageNet model, let's say get 71% accuracy, and you tell me this ImageNet model has a really amazing new robustness intervention. What I'm going to do is, I'm going to look at my baseline and I'm going to see, okay, the baseline would suggest out of distribution, I should get 58% ImageNet v2. If you get 58% on ImageNet v2, sorry, I don't really care about robustness intervention you propose because it doesn't really do anything compared to the baseline. So the big question is, what methods allow you to lift up the baseline of the ImageNet models to the dashed y equals x line? And we know that y equals x is the right target because we did an evaluation with 5 expert human labelers, and humans are indeed on the y equals x line. So if we want to make these ImageNet models as robust to distribution shift as humans are, we want models with what we call effective robustness, the lift above the red baseline. Okay, good. So these were now all of the standard models, 80 of them, about 10 years of computer vision. Let's see if any robustness interventions like adversarial training and so on help here. So in this next plot, this is now 200 models. I did 100 more models, trained on more data or with different robustness interventions. And when you look at this plot, maybe your first reaction is, this just looks like the plot you showed me a minute ago. And this is indeed the right reaction because it turns out that nothing really helps on this distribution shift by a large amount. Like all of these brown points here, randomized smoothing, adversarial training, special forms of data augmentation, they basically fall exactly on this baseline trend. The only models that stand out by a little bit are some of these green points here, which are models trained on more data. On the top right, we have a model from Google trained on 300 million images, a couple models from Facebook trained on 1 billion images, and then this model here, which is trained on the large ImageNet with about 10 to 20 million images. So this is on the order of 1,000 times more data, right, compared to ImageNet. Okay, good. All of this now has been in the context of one distribution shift. We don't have enough time to go through all of these 200 distribution shifts we evaluated this on, but since we mentioned ObjectNet earlier, same type of scatter plot, same models for ObjectNet. The accuracy drop is now much larger. This is a 40 percentage point drop to the dashed line y equals x, but the overall picture is pretty similar. We have a good linear trend here. The brown and blue points mostly fall on the line, and then in the high accuracy regime, the only models that stand out by a little bit are the models trained on more data. Okay, so this was state of the art as of 2020, end of 2020. And then in early 2021, something really exciting happened. It turned out that OpenAI worked on this problem for 2 years, and they made a lot of progress on all of these ImageNet distribution shifts. So this is the CLIP paper. I'm sure many of you have heard of CLIP. Well, we're in a prompting workshop. Of course, you have heard of CLIP. Cool. And sort of like these are the first set results from the CLIP announcement blog post. And what they did is they used our evaluation framework for evaluating the robustness of their CLIP model. Specifically, they compared a CLIP VITL, the largest CLIP model, to a ResNet trained on ImageNet with the same ImageNet accuracy, right? So in the language of our scatter plots, we're looking at a fixed axis value. And then we can compare the accuracies on ImageNet v2, ImageNet R, ObjectNet, and so on. And this is going to tell us the effective robustness. And what you see here is the CLIP achieves amazingly high effective robustness. So 6 percentage points on ImageNet v2, this is half of the drop, and then plus 50 on ImageNet R, plus 40 on ObjectNet, plus 35 on ImageNet Sketch, plus 74 on ImageNet A, right? So you know ImageNet, if you get a small single-digit improvement on these ImageNet-like test sets, this is definitely a nice paper, and CLIP achieved large double-digit improvements. So this impressed me a lot, and I spent a lot of time over the past 2 years understanding what's going on here and trying to improve these models. Cool. So first, to understand this in a little bit more detail, let's look at the scatter plot version of this result. X-axis, again, ImageNet, the OpenAI people used our evaluation framework. Y-axis, they pragmatically averaged the 7 natural distribution shifts, ImageNet, v2, ObjectNet, and so on, onto one value for the y-axis. And then what you see is a couple lines. So the blue line is, again, the baseline of ImageNet trained models. The green points here are the prior more data models. We can forget about the purple line, doesn't matter much. The orange line here is CLIP in zero-shot mode, right? So if you use CLIP without fine-tuning, you get this amazing effective robustness, and you close roughly half of the gap to the y equals x line. And there were sort of like 2 obvious questions coming out of this. Okay, what makes CLIP so robust? And the other one is, what's going on with fine-tuning? Because if you look at this red line here, this is what happens when you take these CLIP zero-shot models and you fine-tune them to ImageNet. So you do make progress on ImageNet. It moves right on the x-axis, but it actually moves a little bit down on the y-axis. And this is only last layer fine-tuning. If you do end-to-end fine-tuning, you sacrifice even more of the out-of-distribution robustness. And then the fine-tuned CLIP models are still a bit better than the prior more data models, but actually not that much. So it seems like that zero-shot evaluation is really giving you a lot of the robustness here. Okay, and then the obvious question is if there's sort of like a trade-off here, zero-shot robustness versus downstream task accuracy where you fine-tune on, can you get the best of both worlds? And this is exactly what we are going to talk about, the second question for the rest of today. I'll just briefly answer I'm not going to answer this. I'm going to tell you the answer for the first question for what makes CLIP robust, because I think this is important to know. And the title of this paper here sort of gives it away. Data determines distributional robustness in contrastive language image pre-training. So what we did in this paper is go through a long list of ablation studies to really carefully tease apart where the CLIP robustness is coming from. So the obvious contender number 1 arguably was language supervision. The whole point with CLIP was we can now combine image and text in our learning procedure. Another big hypothesis was the training distribution. They are trained on a different training set. Maybe this is what's causing the robustness, but there were many more, like training set size, it's trained on more data, loss function, contrastive versus of like 1 out of k classification loss. Test time prompting, obviously, this is now something you can do with the CLIP models. And as Sarah mentioned, a lot of sort of like work went into building the CLIP prompting set. And then model architecture could also be a reason here. VITs, the best CLIP models are VITs. Most of the ImageNet models we looked at were CNNs. But you can do all of these ablations, and the nice thing is you can very accurately pinpoint the robustness that's all in the pre-training distribution. Like none of the other things matter. You can vary them. It does not affect your effective robustness. Effective robustness is only a function of training distribution. Okay, cool. I think there's a whole question around how to build better pre-training data sets that I'm really interested in. But for now, let's continue with the fine-tuning story. And the question was, can we fine-tune CLIP without losing robustness? And the answer is yes. So this was my first paper with a set of really awesome collaborators at UW, Mitchell and Gabriel. The students driving this are fantastic. And this is really their work. Okay, let's just really quickly recap what's the problem with fine-tuning, right? So we have these nice zero-shot CLIP models here. When we fine-tune them, we make progress on the x-axis, but we lose robustness. So we move down on the y-axis. And this is not something only we observed, like the CLIP paper already pointed this out as an open problem. And in the Align paper from Google and Basic paper from Google, other image text models, they pointed this out as an open problem. At the time, everyone was a little bit confused that we had these like really nicely robust large-scale image text models, but then when you fine-tune them, the robustness goes away. So it seems like something really brittle there. Okay, so what do we do to fix this? Let's just quickly recap what we have. So we have two models. We have the CLIP model, which does so-so on our task of interest, but has great robustness. And then we can fine-tune the CLIP model, and we are doing great in task accuracy, but we are doing so-so in robustness. What we would like to do is a model with both. And so the answer is pretty simple. You take half of the CLIP model, you take half of the fine-tuned model, you add them together, and this actually works. This was a big surprise to me. As I said, credit to Mitchell and Gabriel for figuring this out. So we call this a weight space ensemble for fine-tuning. Sometimes things in deep learning are just easier than you would expect. I think also it's a nice indicator for how little we really understand. Okay, so to be fair, they had some really good intuition, Mitchell and Gabriel, from prior work on the loss landscape of neural networks. Specifically, what researchers had observed before, or like what researchers had studied is, when can you linearly interpolate between the training outputs of SGD starting from a certain starting point. And what people had observed is, if you start from a random initialization and then you do two independent training runs, then you have a loss barrier. You can't interpolate in a meaningful way. But if you instead start from a pre-trained model and then you fine-tune 2 times, prior work had already observed that this gives you good points in between. So there's no barrier once you start from the shared pre-trained initialization. And so like the intuition here, basically, once you start out from a pre-trained model, most of your action when you sort of like do fine-tuning happens in a relatively low dimensional space. This is much more well-behaved than the loss landscape at initialization. And sort of like, this is sort of like now a picture for fine-tuning CLIP model here, the star, fine-tuning it twice, and sort of like the color here indicates the test error of the final model, and then you can see all of this is sort of like intuitively happening in one nice basin. And since it's all happening in one nice basin, with the zero-shot model and the fine-tuned models interpolating within this basin is a reasonable operation. Okay, so that's, and sort of like, again, going back to our schematic, now if we look at what happens if I use my fine-tuned model, and then I interpolate with interpolation weight alpha, right? So I do 1 minus alpha times the zero-shot model plus alpha times the fine-tuned model. And now the cool thing is that this interpolation part basically goes up and left, right? So you could think, okay, if I interpolate, maybe I just get the straight line here, but this is not what happens. When you interpolate in weight space, you actually do get those, like this rectangle, weird rectangle interpolation, and you get something that captures the best of both the x and y axis. Okay, so this was still sort of like just a schematic. Let's look at this now on real data, ImageNet, and the ImageNet distribution shifts we've talked about so much. This is an end-to-end fine-tuned model. This is the corresponding CLIP model we are starting from, and this is the interpolation curve. And the cool thing that happens here is that in this example, the final model is actually better on the y-axis, has better accuracy on the out-of-distribution test sets than either the zero-shot model or the fine-tuned model. You could also go a little bit right? If you look at this curve, it curves to the right a little bit before it goes back left. Okay, and then once we had this, obviously, so 9% gains on ImageNet is really nice. Once we had that, we could go through all sorts of different out-of-distribution data sets. and basically sort of like unleash the full robustness clip. And like then basically was state of the art on like whiles, FMOW, cipher distribution shifts, more ImageNet distribution shifts, and so on. So it was very nice. Let's see, how are we doing with time? Probably not great, right? So let's skip over this. There's a nice story around scaling laws here. How we did most of the experimentation on the small models, and then we used effective robustness basically as a scaling law for robustness in order to save on experimentation time, but that's a separate story. For now, I want to briefly highlight this very nice paper from CMU. Sachin may be here today, not sure. They basically combine this weight space interpolation for fine-tuning with another improved fine-tuning idea, and this is currently state-of-the-art for fine-tuning club models. But there's also an obvious question here, okay, like why stop at averaging two models? If we have sort of like this nice basin and all of our fine-tuning action happens in this nice basin, maybe you should just average more things. And this is the idea of the model soups paper. And so the observation was the following, like typically when you fine tune these models and you want to get the best possible performance, you don't just fine tune them once, you fine tune them many times. And then you pick the hyperparameters corresponding to the best accuracy. Okay, this is very reasonable. But again, you're leaving a little bit of performance here on the table, right? Because instead of just picking the best model, what we could also do is we could build an ensemble of all our individual fine-tuned models. Okay, right? That makes a lot of sense. The problem with that is higher inference cost, right? Now, if we have like 10 models and we need to, like the models are already large and expensive to do inference with, the last thing you want to do is you don't want to ensemble them. So this is the problem with these ensembles. We can't get the accuracy gain of the ensemble. So typically people use the best single model, but then they have lower accuracy. And the idea of model soups is again, well, we can just average all the models because apparently that's a thing to do. And the nice thing that happens is you get basically again the best of both worlds. You get a single model that achieves the same performance as the ensemble. And then again, you can go to all the benchmarks and get state of the art, like this was ImageNet state of the art early last year when we released this, and also gives gains on many more data sets. And this has become widely used for sort of like pushing multimodal models to state of the art. Cool, there's sort of like more to this line of work here around fine-tuning a model while preserving its zero-shot abilities. Gabriel, Mitchell, and also Samir now wrote this very nice paper on patching open vocabulary models by interpolating weights. So basically, can you use the model still in zero-shot mode while also having fine-tuned it and still get all the nice zero-shot model benefits, like the flexibility of an open vocabulary model, while also having the high downstream task accuracy. As we said, we don't have time for this. We're already running late for lunch anyway. So let's wrap up now. So conclusion. State-of-the-art models, both in vision and in NLP, can still be improved via fine-tuning, right? The focus for this talk has been all on CLIP, but the same is obviously true for large language models also, right? Like one of the big advances there in the past 1.5 years has been instruction tuning, reinforcement learning from human feedback, and so on. And these techniques do make the models a lot more useful. And the flip side of these fine-tuning techniques is this is also something people have observed in the NLP side, is simple fine-tuning can negatively affect the model in a variety of ways. Like in this talk today, the focus was on out-of-distribution robustness. Similar things also happen in NLP, that you get trade-offs between instruction following and performance on sort of like standard classical NLP tasks. Interpolation is one way in order to get the best of both worlds, at least in a robustness setting, but I think there are still many open questions around fine-tuning. Like one is that the simple weight interpolation, it's cute that it works and still, to me, surprisingly effective, but it also seems naive, right? Like just adding together two models, there's probably something better we can do there. And another thing is a little more speculative now. What I think is interesting, can we remove the need for fine-tuning entirely? Like it's probably better if we set up the right pre-training objective so that we give the right supervision signals during pre-training, and we don't have to do this like slightly awkward first pre-train and fine-tune, where we know that the fine-tune does some damage to the pre-trained model. I mean, this is sort of like $1 billion question now, right? So how to improve the pre-training of these models, but I think it's a really interesting research direction. Cool. So thanks for staying beyond noon, and I'm happy to take questions.
Any question from the audience?
So I'm Imon, and I have one question. Like you are experimenting with flip model, and you are averaging on interpolating weights. But if I want to do this, for example, LLMs, it can be different. Like it's difficult because LLM is very costly to train. Like if I use want to train a ChatGPT, for example. So there is another thing, like another approach can be like to increase the model, maybe some train some layers or some prompt. So do you think in that way, like one thing for me is that if I increase the model, it should preserve the zero-shot modeling ability. And then if I train some layers or some prompt, whatever, something that is not as costly as training the full model, can this be a way to achieve things like zero-shot? Yeah.
Yeah, so there's, okay, I agree with you that working with these models is costly because they're big. I mean, the good thing is also for this weight space interpolation, you don't need to train a model from scratch. It's actually very cheap because you do one fine-tuning run, and then you can vary your interpolation by alpha after the fact. So this, I think overall, this is a benefit of this method, that you don't need to do multiple fine-tuning runs. You do once, and then you have one parameter to tune after that. I think there's a good question whether sort of like parameter efficient fine-tuning methods or prompt tuning methods allow you to do the nice interpolation between downstream task and robustness as well. Off the top of my head, I don't know the answer.
Because I was thinking like, yeah, it's obvious, like you are doing little bit of fine tuning, but if you want to do this with a really large model like Llama 7 billion, for example, you cannot do that in like in a lab, like in a school laboratory, but you can do some add some lab or prompt tuning on this large language model on top of that. So yeah, do you think there is some...
I would push back a little bit on the statement that you can't fine-tune these models. I mean, first of all, I don't think we always have to work on Llama 70 billion. I think you can do interesting science at Llama 7 billion scale. That makes it a lot cheaper. And there's a lot of cool work on efficient fine-tuning of large language models, right? Like, for instance, my colleague at UW, Tim Detmers, he recently released sort of like a repository for 4-bit fine-tuning, and they can fine-tune a Llama 65 billion or 70 billion in an academic setting. So,
okay, thank you.
Cool, thanks.
I think that thanks for the great talk. So I noticed on the interpolation curve, there's like an optimal region of alphas. Oh, sorry, on the there's an optimal region of alphas where the fine-tuned model, when you average it with the pre-trained model, will actually perform better on the fine-tuned task as well. So I was wondering what the intuition to this performance analysis.
Yeah, good question. I mean, so in the end, what we are doing with this weight space interpolation is a form of ensembling, right? And the thing with ensembling is that if you have two different models, they do add up in a complementary way. And like the fine-tuned model and the zero-shot model are just pretty different. So I think this is where some of the in-distribution gains are coming from. I mean, like in the end, the in-distribution gains are not super large, like it's 1 percentage point. I'm not sure if I want to read too much into that, but I think this is gain from ensembling. Like this is similar to what we see in the model soups paper also, right? If you have multiple models and you introduce some diversity, then you see gains from that.
Thank you.
Cool, thanks.
So, thanks for your kind of talk. So we have shown that fine-tuning has shown success over the past few years. So we believe that fine-tuning might deteriorate the performance of generalization. But your talk we have talked about that we can get a more robust model by interpolating the vision model and the fine-tuning model. But in your other questions, we talk about can we remove the fine-tuning, and I would like to know what benefits we're supposed to get by totally remove the fine-tuning.
Yeah, good question. So are you saying, okay, this plot looks great, why do I want even more? And the thing is, it just feels suboptimal to add in the data after the fact. I think if we had the same information during pre-training, the model has access to all the information during pre-training already, and this is just more supervision together at the right time. And we have done some initial experiments in in this model patching paper that I briefly showed, there we looked at how do these weight space interpolation techniques compare to just adding the data into pre-training. Like specifically, you can train a CLIP model, then the CLIP model is surprisingly bad at MNIST. And then you can do this model patching to make it good at MNIST while preserving its zero-shot abilities. What turns out what works even better, by a bit at least, is just adding MNIST to the pre-training data set. So this is why I think there's room for improvement. Thanks.
And Professor, thank you so much for the talk. I want to ask a little bit more about the connection between this parameter space ensembling and general ensembling that's used everywhere. I have kind of a two-part question. The first one is, ensembling is used a lot today for more tabular problems when you're trying to ensemble multiple models of different types and sizes. I wonder if we looked at what happens if we try to do something similar to model suits, but for models that are not necessarily on networks. More on the space.
Yeah, great question. That was a really good question. And I think there has been some follow-up work that looked at that, but I'm forgetting the details right now. I think one thing, there are two things that come to mind. One is that in the tree world, usually the models are already pretty fast for inference, right? Like the weight space ensemble is a way to make traditional ensembles faster. Some level you can summarize it that way. If your traditional ensembles are already plenty fast, there's not really a reason to do this. And of course, if you have a large model, a traditional ensemble will be very slow, so there's a good reason to do this. I think the other thing is that if you want to average model weights, at least the way we can currently do it, the models need to have exactly the same shape. Like, let's say you have two, like if you think of all the trees in a random forest ensemble, they don't actually have the same shape, right? You split on different variables at different times. How do you add these trees together? I think the nice thing about these neural networks is before and after fine-tuning, they have exactly the same shape as a model in a sense, like parameter matrix sizes and so on.
Thank you, that's great. Just a quick follow-up. Can you dig a little bit deeper on the differences that you're seeing between just the traditional ensembling and this kind of thing? I imagine that we use to do some information like doing this smoothing into parameter space.
Yeah, it's a great question. In the model soups paper, we have done more analysis of that. And there's like a lot of interesting results there that I don't have any slides, unfortunately. So at a high level, what we observed is the following, that unless you fine tune with very large step sizes, the performance of the model soup and the corresponding ensemble very closely track each other. And so like the intuition fits nicely with this mental model of a bowl, right? If you fine tune with very large step sizes, you start leaving this bowl region, the nearby region around the pre-trained model, and then things break down and like the weight space ensemble doesn't behave like the output space ensemble. But unless, if you keep the learning rate to reasonable range, including what you need for state of the art, then you stay nearby enough, and then the two actually really closely track each other. There's a very nice scatter plot in this paper, x-axis performance of the ensemble, y-axis performance of the weight space ensemble, and they are very often close to y equals x. The only way that they systematically deviate away from y equals x is the models that you get from like fine-tuning with increasingly large step sizes.
Thank you.
Cool, thanks, great question.
Hi, Professor. Thank you for the nice talk. I have two questions. The first one is about the formula for the interpolation. So we right now it's using like 1 minus alpha alpha. So this kind of linear blending or linear interpolation. Do you think like if we use more sophisticated formulas for the non-linear relationship between these blending, so how that direction?
Yeah, no, this is a great question. I think one good direction here is sort of like not using the same weight for all of the layers, right? This is very crude. This uses one parameter for the entire network. You could ask, well, why should I have layer 2 and layer 25 the same weight? Or like, why should the batch neural parameters have the same weight as your densely connected matrix? And we just observed this already works quite well. There's a nice paper from Colin Ruffels' group where they do what they call Fisher-weighted averaging and have like more sophisticated weighting on different parameters. I think for the vision models, it didn't help much compared to the scalar weights. I think for language models, it helped, but you should check out that paper for the details.
And the second question is related to what you mentioned, that if instead of just one theta, like for the whole model, if we use theta for every layer, like different type of blending for each layer, because in the end part, the relationships are much complex, while in the starting layer, it will be more generic. So
Yeah, good question. I mean, like, give it a try. Maybe you have the right ideas here to improve this.
okay, thank you very much.
Thanks.
Thank you for a great talk. So I got a similar question. And so I thought you, for following up your first two model averaging, to try to find more models, like models later. So can we try average reaction? For example, like how we combine the models of different architecture. For example, you have a thin depth, and each layer, one model has like more maybe channels, the other has fewer. Have you tried to do the maybe a calculation inside the weight tensor to make them weight shape compatible? Or for example, in a recent training of large models, people always try to use some method like parameterization, meaning the actual module, small module on top of existing models to tune them to a new task. So have you see maybe it's possible to just combine different tuning modules together to make it become a more maybe generalizable model across like more diverse tasks or
Yeah, great question. So for the first one, merging models of different shape, I think this is definitely something we've thought about. We haven't worked on that. I think if you reach out to Mitchell and Gabriel, they'll be able to tell you maybe what of the follow-up papers have looked at this in most depth. And then the second question was about combining weight space ensembles with other forms of fine-tuning, if I remember correctly. Yeah, great question. I don't know the answer. I mean, it's possible that you can combine this with adapters and other ways in a good way. Yeah, it would be interesting to see.
I have a recent paper working on it.
Oh, cool. Excellent. Yeah, great. We already have the answer. Even better.
Okay, so let's thank you.
Cool. Thank you.
So we met at